Okay, so this was the first script that we ran. We ran this manually now, and as a result, in the database there is already the stack averaged and its Fourier transform computed. This is before drift correction. So if I move this up and down, only this one file has something, and here we have already entries that this has 80 frames. This is when we processed it today, and the dose is computed per frame. Do we have the total dose? The total dose for this 80 frame movie, oh, it's very high. I wonder if this dose is correct. I think there may be a calibration factor that is not correct at the moment set. Pixel size here for the 8K movie. Okay, if we go back to this, the next script we wanted to run was Motion Core 2. And this uses some settings here and calls Motion Core 2, and Motion Core 2 should soon show up here. Ricardo is hammering this computer. So Motion Core 2 is running in parallel on both GPUs right now here. And the GPUs are fairly bored, and the CPUs are busy with Ricardo's Python stuff, but Motion Core should soon show up here, and then we have TeamViewer with this movie recording. So the question is now, which parameters are used for Motion Core? One way is to look at the verbose output here, and this script puts out the parameters here. Some of the parameters come from here. There's some free parameters. Others are preset, and if you want to see in detail what happens, you just double-click the script as usual, and you scroll down until you find this Motion Core script, and here it is. So there are some parameters hard-coded, like 15 iterations, tolerance 0.5 is hard-coded, but other parameters are free. And if you don't like the parameters that are hard-coded here, you want, for example, 25 iterations or so, you could just edit the script here, or you could make these a free parameter by just entering things here. The patch 5.5, for example, that is a global parameter. So you want this setting, whatever you think is optimal here, you want to run this for all movies from your entire session on your Titan, not only for this one movie, and therefore it's a global parameter. It has this global here. If you change it for one movie, you change it for all of them. Whereas the other parameters, like the electron dose, that's a local parameter. Each recorded movie may have a different dose. So I'm sure this is wrong. Okay, Motion Core is running and will run for a while. After this, we would go to GCTF and so on. This is 80 frames, so this may take some time in Motion Core. And we don't have the output here now. If I go to the hard drive to see where we are here, so at the moment we are running in data, I think proteins, and then ABC work. This is where we work at the moment, and Focus maintains everything it needs in merge, and it imports all the movies into auto. So if we go to auto, so far we had imported these 6 things here. Yeah. The gain reference we need only once for all of them, so it's outside of this. But if you go to this, at the moment we are processing in this number 4. This is where this movie is processed. So there's the TIFF file that was imported and then should have been deleted on the K2 computer. There's the link to the SSD where the unpacked movie is maintained. So it's unpacked into this fast disk, and from there Motion Core reads it and drift corrects it, and the unpacked movie can then be deleted before drift correction. We don't need this. In logs is where all the results files are, these for example. In proc is where the scripts are filled with parameters. So if I go into proc, so the drift correction, or the import, the first import thing, 0em, this script here, this is how it looks when you press the play button. Yeah. Then focus has filled in all these parameters. Before, these were just empty fields, but by pressing the play button in focus, this is filled in and then launched. And so then it's launched as a standard C# script, and all these funny hashmark commands and so are gone. This would be just a normal C# script. So this is the proc scripts. Usually you never touch them. There's a scratch disk, which is not used at the moment. There is a status subdirectory where these little icons or thumbnail pictures are maintained. They're very small. They are later pushed to a web server. Here, they're very small. And then there is logs, and in logs are these files, these results files and logs files. The log file is what is displayed here, and the results file is what is displayed for values and images. So if you look at a results file, for example, the results file from this motion core that is still running. Okay, I look at the results file from the other one. There's the unpacking results file. And this one determines some parameters and defines some images with nicknames, as we discussed. And the GUI will then watch for these and interpret this. There's also now the motion core has finished, so I can look at this drift correction motion core results file. That is the parameters that the script computed. For example, how long is the drift in total, and did the drift decelerate as it should, or did it accelerate, which means your carbon film ruptured or something, and some other parameters like what is the pixel size after Fourier cropping. Before it was half an angstrom, now it's 1 angstrom. So, and then we have the log file and the import drift core log file. This is everything motion core and everybody writes out. And here we see this. Some lines start with two colons in the beginning, like the first line, and this will be a line that is only visible in the lowest verbosity. Everything else is visible at the highest verbosity, and here these with 1 colon, they are visible only with the lowest and medium verbosity. So with this, if you write a program yourself in your own C++ or Fortran or so, and you have the output putting 0, 1, or 2 of these colons in front, you can control under which verbosity setting you want to see this. So this is the raw output of motion core, which is a beautiful program from Zhang in Cambridge or Oxford. So this ran, and if we move this verbosity now to a lower verbosity, because you usually don't want to see all the details each time, you see here the result. So now we have the drift corrected average. You don't see much, and the Fourier transform before and after drift correction. Here we have with dose weighting and without dose weighting. So the dose weighted average is showing the particles nicely, and the non-dose weighted average allows you to fit ton rings nicely. So the non-dose weighted average is fed into GCTF, and the dose weighted one is for G-auto-match and further processing. And then the Fourier transforms of this. There's a drift plot that we produce with a little Python script. You can see it starts, drift starts here and then is fast and then slows down, as we all know. And there's a total length of this trajectory, and then there's a deceleration. It should decelerate. If we go into the library, we now see that the total drift length and the max drift per step and the deceleration, so is all computed. And the jitteriness is a low value in this case. That is if this line is going in zigzag or if it's rather straight. So this is rather straight. Jitteriness is taking every second spot along this drift trajectory and interpolating that with a direct line, and then taking the spot in between and seeing how far that spot will be off, left or right from this direct line. And that's the jitteriness. So how much is your drift trajectory going in zigzag, which means it may not have found the correct drift, or is it a smooth line, which then is very plausible. So the next script would then be gctf, for example, or ctf find. Ctf find runs on the stack, which takes longer, and gctf is amazingly fast and is already done. And there is the output of gctf. And then we can measure the iciness. The iciness is the ratio of, so this is the Fourier transform of this image. The iciness is the ratio of the average intensity in this ice ring here at 3.7 angstrom resolution divided by the average intensity in the low resolution range. And these ranges are chosen so that usually the iciness should be at 1 or smaller. This is the iciness 1 value. If the iciness is more than 1, then usually you have a devitrified grid. Or this movie was from a devitrified location and you can delete this image. The ratio between the second ice ring, which is a second order ice ring, and the low resolution values is iciness 2. This is just for display purposes. Push status data would work if you have the web server configured. On this computer I don't have this. And then you can clean the scratch disk, but you don't have to do this. And then you can run pick particles. This runs gautomatch, which is also amazingly fast with some parameters. Some of them are from here, others are hard-coded. You would have to double-click the script. And there are some output parameters. If I now click on the picture here and hit the button, so I make this smaller, if I hit the button P, I display the positions that gautomatch determined, and the ring contrast is the cross-correlation value that gautomatch puts out for each particle. And you can verify here if the ring diameter corresponds to your expected particle size, and if this is the right particle number, or if it didn't overlook particles or so. And if not, you would have to adjust parameters here. The expected particle diameter, for example, or the cross-collision cutoff value. The others I don't use at the moment. So this would be all we want to do, and I close this image here again. This would be all we want to do. This were all these scripts here. And then now we have these determined, and they are displayed very fast because what we're looking at here is a small PNG file that is made by the scripts from the large images. So you can later scroll up and down here very quickly, and these PNG files are displayed quickly. This is the image overview setting. This is the drift overview, so image and its Fourier transform after drift correction, the drift trajectory, and the GCTF profile. And the last panel is the particle picking with circles indicating where it found particles. This is all what we have now in this mode. In 2D crystal mode you have different things showing up here in tomography, also others. So now we verified that this all works except the dose. One would have to look into the script that computes the dose from the numbers in your image. So the TIFF LCV file has numbers, and they were around 7.5, and you have to find out how your hardware and your serial EM installation encodes average dose into the numbers. And then if you go into this, there is the calculates frame dose subscript, and this is the script where you would have to see that you end up with the correct numbers. We have to see how this is done. So we had an installation where we had to take the numbers in the TIFF file and divide it by 12, and then we ended up with a floating point file that had floating point values that were corresponding to the electron dose that serial EM or the K2 camera was seeing. And what you want is the dose before the sample, not after the sample, so you can deal with this here. And there's different options. You can also define the dose manually, and by just saying, I know what my dose is, it's 1 electron per pixel or something per frame, and then you can type it here. We run this here that we take the counts in the image and then increase them by 30%, which is this factor 1.3, just by assuming that the dose before the sample was 30% higher than after the sample. Motion Core would need the dose to do this B factor filtering correctly. Okay, so in our processing queue, we have 6 images now, and I can just start this queue. Or we can also set this to start always as soon as something arrives, and then this queue is running. And each time one processor finishes, it will check if there's more to do. And at the moment I'm running 2 processors in parallel, but I can set this, as I said, I can set this to much higher. But this number will only be updated here when this one of them is finished. And then in the import section you would say, okay, now we know what to do, and we delete the files after importing, and we go continuously and just launch this. And then Focus would sit there and check the file on your K2 computer, and whenever SerialEM or EPU has recorded a new file, it would copy it over, delete it over there, fill it with these scripts into the batch queue, and the batch queue will fill up, and six of them will always run. So the newest imported one will always go to the top because we said so, and 6 of them will always run, and when one of them is finished, it will pick the next one from the batch queue. You can also clean the batch queue here and move one to the top of the batch queue, or so on. And this will fill up your library. So the library at the moment is running and is processing. But we have only the one that we processed so far. The others are not yet there, but they will come. So here you can see clip is busy unpacking. The GPUs are not yet busy, so there's nothing at the GPU level, and this machine is suffering from Python jobs. So at lower priority, but still. And we said 6 in parallel. Let's see how this does. On the Titan, we now have a computer with a 100 terabyte hard drive and 4 Titan XP cards and 512 gigabyte of RAM, and that machine can run 24 jobs in parallel, and can compute or process with these settings 8K movies, and so about 120 movies per hour, which is about the same speed that we can reach with our SerialEM setup with our K2 camera. So we can record movies of 50 frames up to 120 per hour.